My name's Hillary. I am a senior software engineer on the data science team at Sophos. I also just wrote part of a book on malware data science, mostly the bits on deep learning, which is a type of machine learning, since I really like this stuff. And today I'm going to give you a pretty high-level overview of machine learning and run through a few quick examples of machine learning, and then delve a bit more deeply into deep learning, which is a type of machine learning, since it seems to be all the rage today. So for those of you new to machine learning, which I think there maybe are a lot of you guys in the audience, that's great. This will be a fairly fast introduction since we only have like 50 minutes, but I'm going to try to keep things pretty simple. And to those experts in the audience, feel free to sit back and relax and feel lovely and smug, since you've probably heard most of this before. Also, as a side note, if you have a question or if something is confusing, raise your hand and definitely ask, because I think I have a few extra minutes of time, and probably everyone else is thinking the same thing. So that's great. Okay, so what is machine learning? Let's start from the top. Super generally, machine learning just means any sort of mathematical process that looks at some data and tries to derive rules to do things like predict something about that data, or predict something about future data, or explain that data in some way. So that's really general. You can think of a ton of things that apply here. But more concretely, we can think of machine learning models as just big functions, right? So you have an input, like a picture of an apple, and you apply this machine learning function that we build, and you get some output, maybe like the word apple or a numeric representation of the word apple. And so we can do the same thing with malware. This is actually what the data science team at Sophos focuses most of its time on. We build deep learning models, which are just big functions that take static files, like a doc file or a PDF file or what have you, as input and output a score from 0 to 1, indicating if the file looks malicious. Okay, so the question is, right, what are these functions and how the heck do you make them? Okay, so I want to walk through sort of a toy example to showcase this. So let's say that we're working with HTML files and we want to build a machine learning model that can predict if a file is benign or malicious. So a first step in building a machine learning model is called feature extraction. So say we have a HTML file, we need to represent it numerically in a way that we think will be particularly useful for a model's task. So because this is a toy example, we're going to extract two features, file size and number of HTML elements, and we will very much pretend that these two things are incredibly indicative of file maliciousness, even though that's a lie to a certain extent. And so if we do this across a bunch of known malicious and benign HTML files, right, we end up with a table with one row per file, two columns, and in machine learning lingo, we will be operating in a two-dimensional feature space. So side note, if you've ever heard someone be like, oh yes, our models operate in a 512-dimensional feature space, that just means they probably have 512 columns in their table, and each item is just 512 numbers. It's not that fancy, but we're operating in a two-dimensional feature space, which is handy because we can plot our data. So on the x-axis here, we have file size. On the y-axis, we have number of HTML elements, and every dot in this plot represents our training data. And so we're going to build a machine learning model that looks at this data and tries to do stuff. So again, because this is a lovely toy example, our data is highly clustered, so we see that all of our known malware files are here on the bottom, and our known benignware files are over there on the top. So in machine learning, at least in this example, our goal is to basically build this model that looks at our data and finds a decision boundary, which is this black line here, right? So that when a new example is seen, it can look at it and say, okay, well, this test file is above my decision boundary and it's pretty far away from it, so I'm pretty sure it's benign. I'm not going to block it. And that's the basic idea. So how do you find these decision boundaries? How do you make models that draw these lines? Well, there's a ton of different methods, and sometimes you're not really finding decision boundaries, you're finding clusters or other things. But whatever the method you're using, in general, you can sort of think of the learning process with as sort of a knob metaphor on a control panel. So imagine the shape of our decision boundary is determined by, right, a bunch of knobs on this control panel. And by looking at the training data that we have and turning our knobs into just the right position, which are really just parameters in our mathematical function, we can get a decision boundary that is good. And so to do this, we define something called loss, which is basically like error. So in this example, loss for us could be the percentage of misclassified observations. And so we use various mathematical processes to try to find decision boundaries that minimize loss, right? So this could be as simple as perturbing the line, maybe, so that it goes right here, and then recalculating loss and saying, oh, well, our loss has decreased because now this blue dot is with its friends. So we're happy, so we're gonna keep that little parameter change that was random. But there's different ways to do this. Okay, so that again was a very, very general description. And so I wanna go through a few actual examples of machine learning functions. Mostly very classic examples using our toy data set. Oops, that was wrong. Okay, so the first method to find a decision boundary that I'm going to introduce is very simple. It's just a decision tree. You may have heard of it. So to create a decision tree, we first ask, okay, I have my data, how can I split my data up into two groups by a single feature threshold, right? So we have two features, and we can split up our data by getting a threshold on whatever features. And so all this really means is that we're either choosing a horizontal or vertical line to split our data up into. Once we've done that, we just ask the same question again and split each of these two groups into two more groups, right? So in this case, sorry, what I should have said, and we choose this line in order to minimize loss, right? So we might test out this line and this line and this line and this line and calculate loss every single time and realize, hey, the percentage of misclassified observations is lowest when I draw this line here, right? All the orange guys are over on this side and all the blue guys are over on this side. So we do this again. Sorry, went the wrong way again. We do this again to get 4 groups, and you could do this again and again and again and grow a really big decision tree. But for now, we'll just have 4 groups, and what you end up with is a decision tree like this, which is just a series of Boolean questions. So this is a function with an input, which is a file as defined by our 2 features, and an output, which is what group it ended up in. And so the point is, right, that we can have an input test file and run it through a decision tree and realize, hey, well, in our training examples, when we ran through training examples and it ended up in this, what's called as a leaf node, when it ended up in this group, the files were malicious about 7% of the time. And so our sort of like output maliciousness probability score is going to be 7%. Okay. So that was a decision tree. A bit more complicated than a decision tree is something called a random forest, which is another type of machine learning function. The basic idea is to make a bunch of different decision trees and then have them all vote together to try to decide if, in our example, a file is benign or malicious. So to make a bunch of different decision trees, each tree is first trained on a random subset or resampling of your data set. Right, so instead of just growing one tree like before, we might grow 100, and one tree will only look at some of the dots in our data set, and the next one will look at different dots in our data set. The second special thing about decision trees and random forests is that instead of allowing them to split on sort of like any feature that best minimizes loss in each fork in the decision tree, each fork is only allowed to split on a random subset of the features, if that makes sense. And so the point of this, it's probably a bit out of scope to really delve into why this is super useful, but the basic idea is that you're sort of jumbling up all these decision trees to make them a bit more variable, and then averaging their results, right? And so you sort of get like this smoother approximation to benign ware and malware. So if you kind of like look back here, imagine if these boxes were transparent, a little bit transparent, and you created a bunch of different decision boundaries here, a bunch of different decision trees, and then layered them over. You'd end up getting like a much smoother sort of surface. So that's kind of the idea behind a random forest. Okay, which way does this go? Okay, so another example of machine learning is linear regression. Economists love these for some reason. A linear regression is a super simple function. It's just a linear combination of your inputs, right? So if we go back to our data, we can look at it and say, okay, I want a maliciousness prediction. I want it to be a linear combination of my inputs, file size, number of elements. So we have, right, A, which is a parameter, so a knob on our control panel that we're going to tweak during training, times file size, our first feature, plus B, another parameter times number of elements, plus C, which is a bias term. So we can use, well, in real life, high-level programming languages, but in college life, some matrix algebra to calculate exactly what A and B and C should be. But if you think about it, right, what would happen if A and B are positive? If you have a large number of elements and a large file size, you get a higher score. But we want our maliciousness score to be higher when these are lower because this is where all of our malware is, right? So if we used the math that I won't explain to you, we'd end up getting probably negative numbers for A and B. So that's linear regression, just a linear combination of the inputs. Okay, so all of these examples that I just gave to you are technically under a big umbrella called supervised machine learning, which I did not tell you before. And all that really means is that our training data had known labels that we were trying to be able to predict, right? So we had a bunch of files, and we knew that they were malware, and we knew certain ones were malware, and we knew certain ones were benign. And our goal was to look at the files so that when we see a new file, we can guess if it's good or bad. So especially in the corporate world, this is really, really useful and by far the most commonly used type of machine learning. But sometimes, right, we're asking other questions too. Right, so maybe we have a bunch of HTML files and we know they're all malicious, but we're interested in how they're different. Or maybe we think that there are two malware families, but we don't know which ones are which. So we can use sort of other types of machine learning to learn more about our data, even if we don't have known labels. So these kinds of algorithms are under an umbrella called unsupervised machine learning. And they usually have to do things with clustering or learning how to efficiently compress your data set. And they're mostly basically concerned with sort of figuring out the underlying structure of your data. So the basic difference, right, is to, instead of minimizing loss as defined by the difference between your predicted labels and your real labels, right, we're minimizing loss as defined by some other objective, right, which I'll give an example of. So I'm going to go through a classic example of clustering, which is unsupervised learning, which is the k-means algorithm. So k-means is a clustering function. So say we have all these data points that were gray, and we said, I think there's two clusters in these data points, but I don't really know where they are, and I don't know which observations, which files are assigned to each cluster. So k-means is meant to sort of figure this out and give us these two clusters. So here happy faces indicate cluster centroids. So k in this example is just 2 because it's easier to make slides for. So I've assumed that there are two groups, but k could equal any number like 3 or 4 or 1,000. Actually, no, because we don't have a lot of data, but k is just a parameter that you choose. And this is how you do it. So k-means is just sort of a procedure that you use to cluster your data. So it's sort of like this training process to develop a function that tells us where our cluster centroids are. So to find two clusters, we first pick 2 random points in our feature space, and we're just going to call them centroids, right? So I've picked 2 random points and made them yellow and purple, and these are our centroids. So the next thing that you do is you assign every single data point in your data set to the nearest centroid, right? So all of the purple dots are now assigned to the purple centroid. All the yellow dots are now assigned to the yellow centroid. And next, you update the centroid locations, right? So you say, okay, what is the average location of all of the data points in my domain, right? So the yellow guy is taking the average file size and the average number of HTML elements and then moving towards that spot in the feature space. And then you just iterate a bunch of times. So you just repeat this process. So you reassign all your data points to the nearest centroid. You move your centroid's locations based on the data points that were just assigned to them. You do it again, you do it again, you do it again, you do it again, until you end up with, until you basically reach some stopping point. And so that can be based on a few different things. You can look at your loss over time, so the percentage of, you can define loss by something like the average distance from data points to your clusters or something like that. So you can look at your loss and say, okay, my loss is not really continuing to decrease. You can look at your cluster locations and say, hey, they've kind of stabilized, they're not moving anymore, and I'm going to find that as a stopping point and sort of stop my procedure. And then you have, right, these two clusters and assigned data points. Okay, so that was k-means. So far in this talk, I have described to you sort of the basic ideas behind machine learning and given you a few examples, but all via the lens of a very super simple toy data set with only 2 features and a few dozen data points. So what happens when there is more, right? If we added a 3rd feature, now finding a decision boundary would look something like this. Instead of finding a line, we would be finding a plane, or really a curvy plane, in our 3-dimensional feature space, but the idea stays exactly the same, right? We're just looking at our training data in order to optimize some function that we've decided upon so that we can find a good decision boundary. Okay, so of course in real life, when we were working with hundreds of millions of HTML files and thousands of features, this gets a bit complicated, right? We're trying to find decision boundaries in feature spaces that are just massive. But the objective stays exactly the same. We're just trying to find this decision boundary when we're looking at loss and optimizing parameters to do that. However, this can be really, really difficult, right? Finding good decision boundaries in super high-dimensional spaces, especially when some of the features have a lot of sort of like weird and complex and nonlinear relationships to one another, can be quite tricky. And so this problem comes up a lot in things like image processing and natural language processing and cybersecurity because the data that you're working with is really, really rich. And it's also very context dependent. So if you think about like a pixel in an image or a word in a paragraph, the meaning of that pixel doesn't really transfer to the next image that you see very easily. The meaning of a word is very context dependent. And so it's often very hard to extract meaning that can be projected onto new test samples using machine learning. And so this applies to software security because often we're looking at program files and trying to decide if they look malicious or not, which is sort of similar to natural language processing if you think about it, because you're just looking at a bunch of code, a bunch of language. Okay, so what do you do in real life when working on these difficult sorts of problems with really large feature spaces? Well, ask any data scientist what the best machine learning algorithm or model is, and they will probably tell you it depends, go away, unless they're very drunk. I use that all the time. But well, at least I'm interested in malware detection. And as I mentioned, in malware detection, at least if you're trying to figure out if a static file is malicious or not, that's a really complex problem. And we also have a ton of training data. And so given all that, at least in my opinion, the best machine learning approach you can use is deep learning, which is what the rest of this talk is going to focus on. I cannot yet convince you why this is true without actually explaining deep learning. So I'm going to do that first. Okay. Oops, did it again. Okay, so when you hear about machine learning beating experts at chess and at Go and performing facial recognition and handwriting recognition and language translation, all of these very complex, historically human-centric tasks, that's basically all deep learning, which is just the specific family of machine learning functions. Deep learning is often discussed as this sort of magical, like AI, which is meaningless, like panacea, which is kind of true. But actually, the basic concepts are super simple and really, really interesting. So I want to delve into that. What is actually deep learning? According to most of the internet, deep learning basically just means deep neural networks. So what is a neural network? Well, it's a machine learning function, so there's inputs and outputs. And like the name implies, a neural network is just a network of neurons stuck together. So what is a neuron? Well, a neuron is also just a little function with some inputs and output, and let's figure out what it is. Sorry. Okay, so this is a neuron. There's two components of a neuron. We have our inputs. This could be 100 inputs, but right now we have two, x1 and x2, right? So this could be our two features for a given HTML file. And each input has an associated weight parameter, which is one of the knobs that we're going to optimize during our training process, right? A parameter in our function. And so the first component of a neuron is called the weighted sum component. And I added in some sample values here, but we're basically just taking a weighted sum of the inputs and adding a bias term, right? So this is 1 plus 6 equals 7. We're adding a bias term, which I'm just randomly setting to 1 here, and we get 8. The second component of a neuron is called the activation function. Activation functions need to be differentiable. They mostly are nonlinear. You usually want them to be nonlinear, but they tend to be incredibly simple. As an example, literally the most popular and most commonly used activation function out there is called the rectified linear unit, or ReLU, and all it is asking is, what is bigger, my weighted sum plus bias value or 0? And it returns whatever is bigger, right? So that's the most common one. They tend to be very, very simple. And so in this neuron, right, we have our inputs and our output is just going to be 8 because 8 is bigger than 0. Work. Okay. So as you can see, right, this is a pretty simple function that you can write out on a piece of paper. It's just maximum 0 because we're using a ReLU activation function, weighted sum plus bias equals some number. And this is a very small example of an actual neural network, right? So on the left-hand side here, we have our inputs. So in this example, we have 3 feature inputs. Each of these are sent to a neuron. And based on the weight and bias parameters in each neuron, you're going to get a different output, right? And then all of these outputs are separately sent to this final neuron, which will take the first neuron's outputs as inputs and give us our final output score for the entire model. So you might sort of be able to imagine that with the right weight and bias terms, and maybe with a couple thousand more neurons, a neural network like this one could theoretically take features from an HTML file as input and output some sort of meaningful score that predicts file maliciousness, right? Because if you look back to our neuron, remember the first part of a neuron is just a linear combination of the inputs, which is sort of like a regression, right? So with the right parameters, you can get something interesting going on at least. So how do you get these weight and bias terms? The model optimizes them during training by looking at your training data, right? So I won't go super into the nitty-gritty math details, but the basic idea is that we start off with randomized parameter values. And so let's say that we take a malicious HTML file and we feed it into our neural network, right? So let's say that we have 3 features for a malicious HTML file, 1, 4, and 2, and we know it's bad, so we know the output that we want is 1. We propagate it through our network, and we end up getting a final output here, which is 0.239. And so now we're just asking the question, okay, how can I modify my parameters, right, the knobs, such that our output moves just a little bit closer to 1. And so in real life, we use some fancy calculus derivatives and chain rule magic to calculate this very quickly. But you can sort of think of it in a much more simple way. So you can kind of just think, okay, the model's going to take a parameter here and just move it a tiny, tiny, tiny amount, reevaluate the output, and if it moved in the right direction, then we know that's the direction in which we want to change our parameter, and if it didn't, we know we don't. right? So that's the basic idea. We're just sort of like evaluating all these files and nudging our parameters in just a tiny little bit in the right direction. And then we do this over millions of samples, or in our case, a few dozen data points, but in real life, millions of samples. And when you do this over and over again, you end up getting parameters that create this neural network that give you really, really surprisingly accurate outputs. Okay, so what I've shown you so far is what a neural network is, but the neural network that I showed you before was not actually a deep neural network because there was only a single hidden layer. A hidden layer is basically any layer in between our input and output layers. So I should actually use this laser pointer. In between our hidden input and output layers. So in the previous slide, we had one hidden layer, but when you have many hidden layers, this is called a deep neural network. So this is an example of a very tiny deep neural network. Deep neural networks are really, really powerful because their structure basically allows them to learn this sort of deep nested hierarchy of concepts. And in other words, lower layers basically learn to develop simple transformations of your original input features, and later layers learn to use these representations as their own inputs, right? So this layer might represent a somewhat complex representation of our original inputs. This layer gets to use these guys as inputs. And so if this found something interesting, this layer can use it in different ways to figure something else out. And so that's sort of why they're learning this deep nested hierarchy of concepts, because there's a concept here, and then it's being used in different ways by later layers. And this allows for like super efficient sort of representation of ideas and patterns. So this kind of neural network is able to map out incredibly complex patterns, right? Because later layers are able to take advantage of lower level learned patterns in different ways. And so there's this sort of kind of multiplicative effect. Okay, so I want to do a really quick demo to give you guys an idea of what this means. So let's see if I can click on the right thing. There we are. Okay, so this is a really cool website produced by TensorFlow, which is an open source deep learning framework produced by Google. And it basically lets you build really tiny neural networks with some sample data for fun. So right here on the left, we have laser pointer, our input features, x1 and x2. And here we have an actual neural network that we can build. So we can add hidden layers, take away hidden layers, and this graph here is basically showing our final output neuron, which is going to give us a score, right? So this is our training data, and we want to find some decision boundary. So when I press this play button over here, this website is going to have our machine learning model that we build look at that training data, optimize the parameters, and try to find a decision boundary. So let's press play. And right now this is just one neuron connected to a final output neuron. So pretty simple neural network, if you can call it that. Okay, it does very well, right? Because our data is pretty simple. But what happens when we have a bit more odd data, right? For some reason, let's just say that file maliciousness is defined by number of elements and file size, and there's a circle pattern. I don't know why. Can we find this with one neuron? Not really, because one neuron, right, is just a linear combination of the inputs with a little activation function, so like how is it supposed to find a circle? It can't. However, oops, wrong thing. If we add more neurons, maybe it will be able to, right? If we had two, it can do a little bit of a better job, right? But it's still not got that circle. If we add 3 neurons, it does a little bit better. It actually finds like a nice shape. Ooh, sorry, sore throat. So that's really cool. But let's throw something a little bit harder at it. I want to throw this at it. So this is a spiral shape, and again, right, we're not telling our neural network, hey, look for a spiral shape or look for a circle shape. We're just giving it the data and saying like, please solve this for me. But even with a lot of neurons, it's going to be pretty tricky. If you gave it a ton of neurons, it would eventually find this spiral shape, but it's very, very hard. So if we do this, right, it's going to be tricky and it won't really learn something very fast. However, if we add some more hidden layers, it can start using this like benefit of a deep nested hierarchy of concepts, right? So something's happening, but not great. So I'm going to add some more layers. So I'll add 2 more layers, give it some neurons, like 6 or something, and hope this works. And I'll press play to train. So what I want you guys to look at while this is training are the feature activations in these little blue boxes. So these feature activations are basically showing the decision boundary that each neuron is finding, right? So in this first layer, they're very simple. They're basically just lines because they're looking, it's just a single neuron. However, these later layers are learning much more complex feature representations because they're taking the first neurons as inputs. And so, right, this final layer has the most complex feature representations, and sorry, I'm gonna drink some coffee. It ends up being able to find a sort of spiral shape, which is pretty cool because we haven't told it to find a spiral shape. So that's awesome. Ooh, and if we gave it more data, right, it would do an even better job. Okay, so hopefully that kind of gives you guys an idea of the power of deep learning. I'll go back to the slide deck. Screen maybe? Oops. Okay, cool. So deep learning. One really cool thing about deep learning as well is that it scales like super beautifully with a ton of data. Right? When you throw a bunch of data at a lot of classical machine learning methods, one of 2 things generally happens. One, your computer explodes because it's just computationally intractable. It's not going to happen, right? The second thing is that your model just doesn't get much better. A model trained on 30 million files like does great, and then when you train it on 40 million files, it's like the same model. And that is because, right, there just isn't a ton of model capacity. There's like no more space to fit all these new patterns in, and it's not flexible enough. Deep learning in general is not like this. Like it scales beautifully with a ton of data. Usually you keep on getting better and better and better, even when you've trained it on like 100 million files. So that's super cool, and that's related to this idea of our deep nested hierarchy of concepts. Because, right, we're able to learn these concepts very, very efficiently because there are multiple layers, and we also just have a ton of information able to be stored because of the size of these models, right? So normally when we're actually creating these neural networks in real life, our neural networks have thousands of neurons and millions of parameters, and so that's a lot of information that we're able to compress in there. Other machine learning models often have fewer parameters, and so sort of the size of these models combined with this deep structure allows them to learn super, super complex feature representations and scale with a ton of data. Okay, and I did want to mention, right, this is great for cybersecurity because we have a ton of data. So it ends up working really well. In theory and in practice, at least the team that I work on generally finds that deep learning models are about the best you can do and often blow away other methods. So that's pretty cool. So what I showed you here was actually an example of a feed-forward neural network, which is basically like a cheese pizza. So you can kind of toss on other toppings and get a new type of neural network, but this is sort of like your bread and butter. But there are lots of other kinds of structures for unsupervised learning, for supervised learning, for different types of machine learning that you can look into. Okay, so to sort of wrap up what we've learned so far, machine learning functions. Machine learning models are just functions. They have inputs and outputs, and there are a bunch of parameters that we optimize by looking at our training data and trying to minimize loss. And there's various mathematical procedures to do this. Deep learning is a subset of machine learning, so it's just a special family of machine learning functions. It just means deep neural networks, at least according to most people, and neural networks are just a network of neurons, and a neuron is just a weighted sum and an activation function. And a deep neural network is just a neural network with lots of hidden layers. They're really, really excellent at performing complex human-like tasks, and given enough data, they can have really, really extraordinary results. Okay, so let's see. Do you know how much time we have left? Actually, I can look at my clock. Oh, quite a lot. Okay, good. So I want to give a quick run-through of one of the deep learning models that we've built on our team. This might not be easy to see this, but this is sort of the architecture of our short string detector, which we use for URL classification. So we give it a string like, Facebook.com, and it looks at it and tells us if it thinks it's suspicious or not. So we generally pair this with our HTML detector for browsers. So I'm going to run through the structure of this neural network more to give you an idea of what production neural networks sort of look like, and less to fully understand what's going on. So if you do not understand a word, that's okay. It's just sort of a basic idea. So first we take a URL string as input. It's one-hot encoded. We apply a learned embedding that's learned during the training process. So instead of a one-hot encoded character vector, this is transformed to a 32-dimensional feature vector, so that things like uppercase letters are closer in this 32-dimensional space than lowercase letters are, right? So they cluster. Next up, we use convolutional neurons, which is a special type of sort of layer of neurons, to extract n-grams. This is usually used in image processing because you sort of take a sliding window of your data to really make it focus on localized portions of your data. And so we're using it on an actual string to sort of extract n-grams. These feature activations are summed up and sent to a bunch of fully connected layers. Each layer has about 1,024 neurons, right? So that means that there's about 1 million parameters for each of these connected layers. It's sent through 3 of those, and then finally aggregated through what's called a sigmoid output neuron to give us a final suspiciousness score. So that's it. What's really cool is that this entire sort of design can be defined in Python just with this code, right? So you don't need to understand any of this code, but that entire design is right there in just a few lines of code. And so what's cool, right, is that in 2018, you can just use super high-level packages and programming languages to sort of design these models and test them on your own computer. Maybe not super quickly, and maybe not with 100 million files without a bit of money, but you can try out this stuff. So we actually, for this model, this is defined in Keras, which is a wrapper to TensorFlow, which is also available in Python, which is that open source machine learning framework produced by Google. Okay, so I want to demo this real fast, if we can. Okay, so I'm going to load up my model right here and test out some URLs. So I don't cherry pick. Feel free to shout out URLs that you want me to test. I can Google them to get the exact URL. As an example, I don't know if this is going to work, but you can, put in some URL and it will give us some output, right? Like 0.005. So this is very close to 0, so our model thinks this is probably not going to infect my computer. However, if you give it something a little bit more suspicious looking, like Amazon login credentials, right, it's going to give you a high score. So yeah, any suggestions, anyone? I don't know, paypal.com, maybe paypal.com/login/ lots of random letters. I don't know, gives you a high score. So the basic idea, right, is that it hasn't memorized like a bunch of URLs. It's like figured out what looks malicious in a URL. So that even if you give it a URL it's never seen before, it can say, hey, it looks like it's asking you for credentials, and it looks like this is kind of like the PayPal word, but a little bit different. Or like it looks like, oh, I didn't put HTTPS. It looks like this is HTTP instead of HTTPS, right? So this is 0.99 because there's not an S, and I hope this works. When you add an S, it's much safer, right? So stuff like this. So that's the basic idea. Yeah, let's see. I'm gonna go to Reddit and get a random URL. Let's see. What's something that's safe for work? Let's go to machine learning. Maybe. Oh, I didn't put it. Oh gosh, you're right. Shows me I need to Reddit more often. Okay, so this is blue, so I promise I haven't, oh, there's no link. I haven't gone to these before. So.
What about that XRV?
The XRV? Sure. Where's that?
It was in the link you had near the top.
Oh, really? Oh, near the top. Let's see.
No, in the going into the one you were in.
1, 2, or 3?
Let's go with
3. Okay. Let's do this. There's a link somewhere?
Maybe it's not that one. There's one of those three, one of the top comments had it.
Oh, really? Okay. Let's check it out. Okay, cool. Alright. Let's see what happens. I hope I won't get fired. Okay, very low. Yay. And Reddit itself, let's see. Hopefully it will be very, very low. Yeah, so this is the basic idea behind these models. We train them on like hundreds of billions of URLs so that they can learn these patterns and figure out that this is not gonna hack a computer. Okay, so let's see if I can go back to this. A bit extra time for questions. So, okay, so that's actually the end of all of my talk. I'm a bit early, but if you want to learn more, I highly recommend things like YouTube. 3 Blue 1 Brown is like really, really awesome at explaining neural network theory. Wikipedia, Coursera. I also just helped write a book, so that's fun. What have you. Yeah, so feel free to learn. It's very, very fun. And that's it. So yes, any questions? Yeah?
This is probably really basic.
That's great. I like those.
Is this on? Oh, okay, great. This is probably a really basic or even dumb question. I'm having trouble understanding where like hidden layers come in. How do you test or detect for that, or how do you set them up?
Okay, so yeah, definitely. Let me go back through this. Okay, so what you do is you're not sort of growing hidden layers during the training process. You sort of define your architecture and then you train, right? So yeah, so it's sort of like a hyperparameter. So you're saying like, I want a deep learning model with like 7 layers. Yeah, and then you train, and then the parameters in that neural network are optimized. Oh, sorry, 1 second. Yeah? The actual structure of the model, or?
Yeah, it's like looking for a line of best fit.
Yeah.
Right? And those just sort of organically happen as a consequence of that.
For the actual design of the model, or like just parameters?
Really general way. I don't know if I'm asking it correctly.
So,
Just not understanding where they come from, basically.
the optimized parameters?
Hidden layers, do they self-generate as a consequence of what you ask them to do?
Okay, yeah, no, so they don't self-generate. So like in Python, in Keras, right? You'd say, I want my first input layer, and I want it to have 3 neurons, and then this is going to feed to a new layer, and I want it to have 4 neurons, and this is going to feed to a new layer with 4 neurons, and this is going to feed to a new layer with 2 neurons. So you define that, right? And that's fixed, and it doesn't change during the training process. And each of these neurons, right, has their parameters, their weight and bias terms. And then during training, all we're altering is just these parameters, right?
Okay.
Yeah. Okay, cool. Cool. Oops. Yeah, for sure. Did you have one? Or?
Okay. Oh, sorry.
Yeah.
As you're training the model, do you train the first layer first, and then is it important to hold that fixed as you train the upper layers, or is that order important?
That's a great question. So it's all trained at once with math. Yes. Google backpropagation, probably watch a YouTube video to learn more. But basically we use the chain rule and some really fun derivatives math to sort of calculate which direction all these parameters should be pushed sort of at once. Yeah.
As a follow-up to that, how do you debug incorrectly trained layers, or is that not a thing?
Incorrectly what layers?
Trained layers, for example, you trained this deep net and you found something odd in it, so you want to debug it, or is that not possible?
So I guess it depends what you're looking for. You can definitely look at the feature activations, so you can kind of debug it to a certain extent, but deep neural networks are famous for being kind of black boxes, so it can be very difficult, especially if it's if it's a hidden layer, you don't really fully understand what the inputs are or the outputs, so it can be tricky. But yeah, you usually can just do things like, did my model get better when I added a hidden layer? If it did, that's great. If it didn't. Okay, you had one?
In
Sorry.
the really simple TensorFlow that you did,
Yeah.
What did you input into that? So did you go through and configure each neuron with what the weighted average should be, and then because you were just going through saying plus, and it looked magic. But I'm going to assume that you had pre-configured those.
It's actually, so it's really simple. In Keras specifically, you basically work in layers. So usually with neural networks, you have layers of neurons. And so what you generally do is say, I want a layer of ReLU neurons with that ReLU activation function, and I want there to be 1024. Right? And then you just say, I want another layer, and I want it to be fully connected, which means that every single neuron in this layer is connected to every single one in the next. So that's why you can design these with amazing speed, because you're not actually defining every single neuron.
Right, you're not going through choosing each individual neuron with the with the weighted average or whatever that you're doing.
Yeah. Okay. I mean, you could, but usually you're working with big layers with thousands of neurons, just because, that's what you want to do. So it makes things a lot easier.
So to your previous question, I think Richard may have given a talk online last year at Ground Truth about as a way to understand what was happening inside your neural net model. So that might be a good reference.
Yeah. There are definitely some really cool ways to, Line is related to that.
Gave a talk on it in this track last
Oh, yeah. Did he do Line? Yeah, that was great. We actually tried out some of those methods on our team, and it was super awesome. We tried it on the URL model to see
this is Richard Grant.
Substrings. Okay, cool. Yeah, for sure. Any others? Yeah?
You said the activation function might be differentiable.
Yeah.
And you mentioned use derivatives to optimize parameters.
Yes.
So, but then the example you gave was just using trial and error on iterative.
Yes. So trial and error is a lie, because that's not efficient. It's just a really nice way to think about it. Yeah, so basically if you think about every single neuron, it's a linear combination of the inputs, which is differentiable, and it's a differentiable activation function, and you're just sticking these guys together. So a massive deep learning network is all differentiable. So as a result, we can basically just use chain rule magic to calculate how will my output change if I change a certain parameter, because it's just a partial derivative. And then we use chain rule magic to calculate that super efficiently by going backwards layer by layer, which makes it super fast, and that's why we can build these. Yes, sorry, that's why. Yes, sorry. Yeah?
First
of all, thanks for your talk. It was a really good primer, like your background and
Oh, yeah.
this
Thanks.
kind of thing. So there was like one of these things that can be quite powerful. Do you think this is like you need to have a background in data science to maybe get some use out of this kind of thing? So say like you can program, you can script and that kind of thing. Do you think you
I mean,
get some
a background in data science is really nice. A background in like probability theory is like lovely, and I think will always help you out. But I think if you're smart and you're ready to learn, like anyone can really do this, especially if you have a background in programming. So yeah, they're really, I don't think there are barriers. Like honestly, there's so many amazing resources on the internet nowadays that like if you really want to and you're willing to spend the time learning and are interested in this stuff, like you can totally do it.
apart from the YouTube channel that you recommend, is there another particular resource that really stands out and something that was really
Let's see.
like
So there's a visual introduction to machine learning, or deep learning, which is really good. I think that's what it's called. So I'd recommend this. It's like a visual blog with like a ton of really awesome like D3 based visualizations, which a book, although, yay for books that I helped write, a book can't do that. So that's really awesome. That's super cool. Yeah, so I think this is like an introduction to machine learning, I guess. I forget if it goes into deep learning later. Maybe it doesn't. This is a really good introduction to the basic ideas of machine learning. I think the Blue Brown YouTube author is really awesome. If you're interested in summaries of machine learning papers, I highly recommend the morning paper. He has like super awesome TLDRs of complicated machine learning papers.
The what paper?
The morning paper. Very smart dude.
like a Twitter handle or
It's a blog, so the morning. Yeah, it's just a website with a big blog on it. This guy just reads scientific papers from various different domains, including deep learning, machine learning, and summarizes them in like really nice blog posts. Other than that, I think those are probably my best recommendations. Yeah. Any other questions? Yeah. Oh, sorry. Yes.
So the data sets that you're working on are trying not to be detected. They don't want to be trainable. Mm-hmm. So do you just retrain as you recollect more data into your data sets, or are you also adding attributes over time?
So we try to train on really, really fresh data. So yeah, we often are training on like 30 days of never before seen files because we want to focus on being able to detect files that signatures will miss. So we definitely focus on that. In terms of altering, you're asking if we like alter our feature space, like the features that we're extracting? I think we do that a lot less often. One benefit of deep learning is that you don't actually have to spend a lot of time working on like complex feature extraction, because if you give a deep learning model like pretty raw features, they'll do the feature extraction for you, right? Because they're learning these complex feature representations. So you don't need to say like, oh, here's like the length of my file, or like, the number of A's in my file, if that meant anything. Like it'll figure that out for itself. So at least for us, that tends to be pretty stable, but there's always room for improvement for sure. Yeah.
What are some of the limitations of machine learning, if you ran into any personally?
Yeah. So deep learning in particular, well, and machine learning too, there's something called adversarial attacks, which are sort of a big hole in machine learning defenses. So malware authors can definitely, if they have access to sort of a bunch of inputs to one of our models and the model's answer, there are certain ways to sort of craft other models to craft inputs that will get the wrong answer. And so that's a big problem in sort of machine learning and malware detection that a lot of people are thinking a lot about. And another good reason why you really can't just have machine learning. You really want like machine learning and signatures and like other methods of detection. So that's probably the biggest hole I can think of.
Do you know a use case where I should not use deep learning?
A use case where you cannot do that's well. So when you don't have a lot of data, deep learning probably is not the best bet. If you really want your problem to be explainable, also probably not your best bet. If you're really, really concerned with just results and you have a lot of data, then deep learning is a great idea.
I know Sophos is probably doing an excellent job at deep learning and machine learning tools, but can you know of any other industry players that may be doing a decent job, in your opinion?
I think there are a lot of players out there that are doing a great job, but I also do not really have access to their results. So I plead the fifth, but I think lots of people are working on a lot of super interesting things. But I also like my team, so. If we have time.
Do you use any AutoML? Thanks for your talk. Do you use any AutoML strategies to train your model, or?
Automated strategies, like to optimize like the structure?
Yeah, and there is a lot of research in the recent years about
Yeah. So we've done like automated hyperparameter searches to a certain extent, but when you do like Google's tried like building a machine learning model to like predict the optimal structure of a neural network, and that's great, but it also costs like a lot of money because training neural networks when you're training them on hundreds of millions of files is quite expensive. Yeah, so we've mostly limited it to like hyperparameter searches and not anything more complex, purely because we don't want to spend like $2 million training our next neural network. Cool, I think that's all the time we have, so thank you so much. Feel free to hit me up afterwards with questions.